Okay, we're working with something called function notation, which is new to you guys. This question, essentially, okay, first of all, it's talking about the height of a rocket in reference to time. Okay, so t is representing time, and the height of the rocket changes depending on how long it's been in the air for. Okay, so this height, or h at t, represents the height of the rocket depending on how long it's been in the air. And t represents, like we said, our time. So we're going to put that up there for you. T is time. And h at t is height. Now, I know you guys aren't used to seeing things this way, but technically these are just both variables. Okay? Our t is a variable, and our h is a variable. Is this guy serious? Okay. Another way you can show this, our h at t could also be y is equal to negative 4.9 t squared plus 19.6 t. Actually, you know what we're going to do? We're going to replace t with the variable x. Thank you.
Cool.
So, the only difference here is essentially the variables we're using. Now, the reason, okay, and think of h at t as our height and our x at being time. The only reason we're writing it this way is so when we go to plug values in, we can know exactly what we're working with. What we'll eventually do is we'll start to solve height for a specific number, and that specific number is going to represent time. It's going to replace t, and we're going to put it throughout the equation. Okay. Now, what they've asked us to do in this question is model the flight path of the rocket. So since we so far don't know very much about quadratics, what we're going to do is we're going to create a table of values to solve this. So we're going to bring out our table of x and y values. Oh, whoops. Let's try that one more time. Okay. So what we're going to do is, again, instead of using x and y, we are going to work with h at t, or height and time. So this will be our time, and our height will be dependent, right? Time is the independent variable. Like I said, we can't influence time. So depending on how long the rocket, or how long after it's been shot the rocket is, depends on its height. Eventually, gravity will take it, and it'll start to come down again. So the very first thing we're going to want to do is solve time when time is 0. Okay. So what we're going to do is we're going to take that equation, and we're going to find h at 0 instead of h at t. Okay? So I'll rewrite the original equation so you guys remember what it looks like. H at t is equal to negative 4.9 t squared plus 19.6t plus 34.3. Okay? So what we're going to look for is we're going to look at h at 0. So when time is 0, how high is this rocket in the air? So we replace t throughout the entire equation with 0. Okay? 0 squared times 49 is going to be what?
0.
19.6 times 0?
0.
And then plus 34.3? 34.3, good. So the height of this rocket when time is 0 is 34.3, and let's say it's in meters. So what does that mean? Time at 0. Where is the rocket right now?
34.3 meters.
Okay, we know that, but in terms of being fired, have we shot it yet?
No.
No, right? It's sitting whatever the launch pad or wherever it is, and it's 34.3 meters above the ground, so maybe it's on the edge of a cliff or a building, something like that. But we know the rocket is starting above the ground. We're assuming 0 is ground level, okay? So we know where it is after 0. So then what we're going to try to figure out is at 1 second.
Oh, sir, equal up. Just like
Yeah. At 1 second, where will this rocket be? So we're going to look at h at 1. And we take the exact same equation, and we plug in 1. We're going to work through this together. Now, hopefully you guys have calculators with you. We're going to go through this quickly. 1 squared is 1 times 4.9 is negative 4.9. 1 times 19.6 is 19.6. Plus 34.3 And even I am going to bring up a calculator here to quickly do this. I know Andy can do it in his head. Okay.
I think it's Andy doesn't know what they come to in his brain.
There you go, 49. Okay? So, what has happened after 1 second? What direction has this rocket gone? Up. Okay? So we know it's not falling off the edge of the cliff. It's actually risen in height. So we're going to follow this until essentially it hits the ground. We're going to try going second by second. Okay? So h hat 2 is the same idea. We'll plug it in, but this time I'm just going to try to quickly solve it. Plus 34, blah, 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 blah. And what we end up here is that h hat 2 is going to be, and I think I have it here. 53.9. Okay? So if we were to carry this out, we would eventually find, we'll plug in the other values for you. At 3, we're at 49 again. At 4, we're at 34.3 again. And then 5 is 9.8. I know I didn't make this chart long enough. I'll move some stuff down. So essentially what we need to do is continue this pattern. 5 is 9.8. And then at 6, we're actually at a negative number, negative 24.5. So let's talk about what this probably means.
It's already coming back on.
It's hit the ground. Remember, 0 is ground level. So we fired from 34.3. After 4 seconds, the rocket's now below from where we fired it. And at 6 seconds, forgot to put the negative sign up, it's supposed to be below the ground. But we know this, unless this rocket is some type of drill that goes into the ground, it's hit the ground between 5 and 6 seconds somewhere. Okay? But the very important part about this is I want you guys to get used to this function notation. Okay? Remember, this is almost essentially saying a y value, but with the function notation, it allows us to look at what values we've plugged in for h.
Is 6 24.5?
Negative 24.5.
Negative?
Yeah, it's supposed to be negative. All right. So function notation is what I want you guys to get used to. Instead of using y on one side, we're using the height in reference to another variable. And that variable will be what's inside the brackets. We use t in this case. It could have been technically any variable we wanted.